Back in 1936, Alan Turing wrote a paper. In it, he solved a problem that had been puzzling mathematicians for ages. Oh yeah, and along the way, he basically invented theoretical computer science. Let's have a look. Welcome back to Attic Philosophy. On this channel, we're looking at all areas of philosophy, from the abstract, metaphysics and logic, right through to applied social issues. In this video, I'm going to be looking at Alan Turing's paper on computable numbers with an application to the Entscheidungs problem. Basically, this is the paper where he introduces Turing machines as a way of proving that first-order logic isn't decidable. And in doing that, he basically instigates modern theoretical computer science. Okay, so let's break all of that down. What problem was he trying to solve? How did he solve it? What's a Turing machine? And what have they got to do with the development of computer science? Okay, so let's talk about one of the main contributions that Turing made. It was in his paper on computable numbers with an application to the Entscheidungs problem. Okay, so what is all of that and what did Turing do? So this goes back to the German mathematician David Hilbert, who at the turn of the century was the biggest mathematician in the world, the most famous mathematician. And he set out a number of problems or questions that other mathematicians would try to solve. In 1928, he posed the Entscheidungs problem, or the decision problem. So it goes like this. Is there an algorithm which, if you give it an arithmetical statement, it will give you a correct answer? Yep, that's true, or no, that's false. And because of various results in logic, that basically amounts to the question of, is there an algorithm that allows us to deduce that answer from axioms of logic if in fact it is an arithmetical truth? So if in fact it is deducible, can we automatically deduce it from the axioms of logic? Turns out the answer's no, but it took real ingenuity on part of Turing to come up with that answer. So before we get on to how Turing did that, let's just spend a minute and think about, why is that an important question? Well, we have to go back a bit to the turn of the 20th century when mathematics, theoretical mathematics, was in kind of a little bit of turmoil. People had found lots of paradoxes. There was this general feeling that the foundations of mathematics wasn't on good footing. And a lot of mathematicians and philosophers, so people like the German Frege and Bertrand Russell, they were trying to establish mathematics on sound footing by reducing it to logic. Okay, so this program was called logicism, reducing mathematics to logic. And the idea is logic is on firm footing. It's all clear. We do logical proofs. So if we could transform mathematics into this purely logical procedure, then we could avoid all the paradoxes. Okay, but in order to do that, we first needed to know just how much of this careful, algorithmic, logical reasoning could we do? Okay, so this is where the decision problem comes in. Just how possible is it to derive truths of mathematics, truths of arithmetic from the axioms of logic? Not by guesswork or intuition, but just by using an automatic algorithm. Okay, so that's why the decision problem was important. Okay, so when we're thinking about an algorithm here, we're thinking about an automatic procedure that follows a definite set of instructions. So if you are following that algorithm, you don't have to use any ingenuity or intuition or understanding even. You just follow the instructions and you take an input and you do some stuff and you give an output. So that's why they wanted the existence of algorithms for solving problems in logic and mathematics. So Turing showed us that no, there isn't always an algorithm. There isn't always a solution to the decision problem. Now, Turing gave himself a really difficult task here, right? Because he's trying to show that there is no possible algorithm that solves a particular problem. How do you do that? How do you show that no algorithm can do it? If you're arguing the other way and you want to show that, yeah, there is an algorithm that does it, it's kind of easier. You just provide the algorithm. So if I give you an algorithm that does something, I have proved that the algorithm exists. But if I want to prove that no such algorithm exists, how on earth can I do that? It's not like I can go through every single algorithm because there's infinitely many of them. Turing came up with a really, really clever argument. So the first step was to basically make the notion of an algorithm official, mathematical, formal. And he came up with the idea of what he called a universal computing machine, a machine that he described mathematically that could do anything that any algorithm could do. Okay, this is the notion of a Turing machine. So let me describe that for you right now. A Turing machine is basically something like this. So we've got a tape. On the tape, we have ones and zeros written, and we might also have some spaces or some B's for blanks. And the idea there is we can code any problem in mathematics in binary strings of ones and zeros. Then we've got something that is going to read symbols on this tape one square at a time. So this little box here, it's going to run up and down the tape and it's going to look at one square at a time. And it's got a state. And you can just think of that as a number, like imagine a big wheel with all numbers around it. And that records what state this machine's in. Okay, so what does this machine do? It has a program. And the program has a number of instructions in it, and they're basically super simple. They say things like this. If you're in state number 152 and you're looking at a 0, then do the following things. Maybe you're going to change the 0 to a 1. So the Turing machine, it can rub out and write new symbols on the tape. It can move left or it can move right. And then it can move into a new state. Okay, so if we imagine this state as a big wheel with counters on it, you basically just kind of move the wheel round until you're in state number 381 or whatever. Super, super simple. But Turing's idea was anything that can be done by any algorithm can be done by a machine like this, by a Turing machine. Now, that's not something you can prove, so that's called the Church-Turing hypothesis. Anything that can be computed can be computed by a Turing machine. Pretty much everyone believes that that's true. The notion of computation is kind of informal. There isn't an exact definition. You can think of this as a definition of computation. Okay, this, what the Turing machine's doing, that is what computation is. And then it becomes not just a hypothesis, but a theorem. So how would Turing show that no Turing machine could solve the decision problem? Okay, that's what he's trying to do. He's trying to show that no algorithm can solve it by showing that no Turing machine can do it, because if an algorithm could do it, a Turing machine could do it. First of all, he showed that a Turing machine can't solve another problem. It's called the halting problem, and we're going to get to that in a bit. And then he showed that, well, if you can solve the decision problem, then you can solve the halting problem, but you can't solve that, so you can't solve the decision problem. The halting problem, it's really cool. Okay, so let's have a look at it. We've got all these Turing machines, right? We're gonna take a Turing machine with its program, and we're gonna put a tape into it, and the Turing machine's gonna do some stuff with that tape, and the output will be whatever's written on the tape when the machine halts. So Turing machines, they have a special state. Just think of that as the halting state, and if they get to that state, it stops. And then we say, it's halted. A machine won't always get to that state, okay? A machine might halt, but it might not halt. How could a machine not halt? Well, suppose it had a really daft program like this, okay? You've got these two instructions. If you're in state 1 and you see a 0, then go into state 2 and write a 1 there. If you're in state 2 and you see a 1, then go into state 1 and write a 0 there. Okay, that's a pretty daft program, because if you do end up in this state, then you're going to go into this state, and then you're going to come back here, and you're going to go into this state, and then you're going to go back here, and these instructions will just loop around forever. Okay, so if you get caught in this loop here, you're never going to get to the halting state. So a program like this, if it does see a 0 in state 1, it'll just loop forever and it won't halt. So sometimes a particular Turing machine with a particular program with a particular string on the tape, it won't ever halt. Some machines will halt if they get a certain input, okay? So it'd be nice to know, if we're going to give this input to this Turing machine, is it going to halt or not? How could we tell that? Well, we could run it and see. Maybe it takes too long. It'd be nice to be able to kind of work it out with an algorithm. Oh, an algorithm, that's what Turing machines do. So it would be nice to have a Turing machine that can tell us, if I've got this Turing machine over here and I put this tape into it, is it ever going to halt or not? Could I have a Turing machine that will tell me that? Turing proved that there can be no such machine, because basically it would be contradictory. And his argument for that is really, really, really cool. So let's have a look at how it goes. Let's suppose we did have such a machine, okay? So let's suppose that we've got this machine Don't care about how it works. Let's suppose it's magical or whatever. Let's just imagine that there exists this machine. And what we're going to do is we're going to feed it with information about a Turing machine and an input. And we ask it a question. Is that Turing machine going to halt with that input? Basically what we're doing is we're taking the Turing machine, we're coding it up on a tape, and then we're sticking this input tape at the end of that tape, and we're putting it all into the halting machine, and we're going to get an answer. Yes, that machine's going to halt, or no, that machine's not going to halt. Turing then gave a really nice argument that shows that this little box here is impossible, and it goes like this. Well, if that machine is possible, then we can fiddle about with it and add a bit more and end up with something like this. So what we do is we take a little machine that just goes around in a loop, like the program we talked about a minute ago, and we connect it up to the yes output. So if this machine answers yes, we go into this machine, okay, and we just loop forever. And then we connect up the no output to a machine that basically does nothing apart from halting. So it just basically jumps straight to the halt state. So if this machine answers no, then we just halt straight away. Obviously, if that machine exists, these machines exist, so the whole thing exists. Okay, so if that's possible, then all of that big machine is possible. Here's the problem. Suppose we code up the whole machine, this whole great big thing here. We write that description down on a tape and we feed that tape in here. So we basically feed a description of this machine into itself. And we say, okay, we give you some input. Are you going to halt or not? What's the machine going to do? Well, if it is going to halt, this machine will say yes, but then we go into a loop, so we don't halt. So if the machine would halt, it wouldn't halt. Okay, so maybe it's not going to halt. But if the machine doesn't halt, this part of it answers no, and we go into this bit, and it does halt. So if it doesn't halt, it does halt, and if it does halt, it doesn't halt. It's a contradiction either way. This machine is impossible. It's contradictory. And because this thing is contradictory, but these bits are possible, it's this bit that's the problem. The halting machine just can't possibly exist. It's impossible. It's contradictory. No Turing machine, no algorithm can solve the halting problem. Okay, that's super important. That's a really important result because it comes up right the way through computer science. So the halting machine is impossible. The halting problem is undecidable. That is a super important result and it comes up right the way through theoretical computer science. Here's how it gets used. Suppose you've got some problem you're interested in, okay, and you want to show is it solvable or not. Well, here's a way that you can show that it's not solvable. You use what's called reduction. You reduce your problem to the halting problem. So you show that if there is a solution to your problem, then there would be a solution to the halting problem, but there isn't a solution to the halting problem, so there's no solution to your problem. That's a general strategy that computer scientists use all the time, every day. Here's how Turing used it to show that there's no solution to the decision problem. He basically said, yeah, look, if there is a solution to the decision problem, then we can solve the halting problem, but we can't solve the halting problem, so we can't solve the decision problem. So all he needed then is just a little bit more argument to show that this bit, basically, if you can solve the decision problem, then you've already solved the halting problem. He had a really nice argument for that, and it goes like this. So we can code up Turing machines in logic in such a way that if we take a machine and it is going to halt for a given input, then that description of the machine will logically entail that the machine will halt. That symbol there means logically entail in formal logic. We've got this description of a Turing machine, and our description of it will entail that the machine will halt if in reality that machine really would halt. Now suppose we have a decision procedure for logic. In other words, suppose we have a way of testing whether any premises really do logically entail a conclusion. Well, that just gives us a way of testing, an algorithm for testing whether a description of a machine entails whether or not it will halt. But that solves the halting problem, right? Because that procedure for working out logical entailments would then basically tell me whether any machine described in logic will halt or not. So if we solve the decision procedure for logic, we've solved the halting problem. We can't solve the halting problem. So we've proved, Turing's proved, that there's no algorithm which tells me in logic whether this conclusion follows from these premises. There's no solution to the decision problem. Okay guys, so there you have what Turing managed to achieve in this amazing paper way back in 1936. If you're interested in going into more detail about Turing machines, what they do and how they contribute to theoretical computer science, I'm going to be going into more detail on that in a follow-up video, so check back for that. If you're finding this stuff interesting, consider subscribing to the channel. I would really love to have you on board. I really appreciate all your comments. Thank you so much for watching. I'll see you next time.